What if I told you that right now, as you're watching this video, something is racing toward Earth at impossible speeds? Something so massive, so unprecedented, that Harvard scientists are calculating disturbing probabilities about what happens next. Between November 21st and December 5th, there's a window, a specific time frame where, if certain theories prove correct, everything we know about our place in the universe could change forever. But here's what's really happening while the world watches the skies. This isn't just another conspiracy theory. This is about 3I/Atlas, officially designated as the third interstellar object ever detected entering our cosmic neighborhood. While NASA maintains it's merely a comet, a growing number of respected researchers, led by Harvard astrophysicist Avi Loeb, are suggesting we might be witnessing something far more extraordinary. Something that challenges everything we thought we understood about what's possible in our solar system. Tonight, we're diving deep into this mystery. We're examining the evidence, exploring the science, and uncovering 10 groundbreaking discoveries that are converging at this exact moment in history. From reversing aging in living organisms to achieving fusion breakthrough that could provide unlimited clean energy. From confirming the 6,000th exoplanet to documenting unexplained phenomena in our own skies. These aren't isolated events. They're pieces of a larger puzzle that's starting to reveal a picture nobody anticipated. Before we journey into what's really happening with 3I/Atlas and these other world-changing discoveries, I need you to do something important. If you value understanding what's actually happening in our world right now, hit that like button. It tells me you want more content like this, deep investigations into the science and mysteries that mainstream media barely touches. Subscribe and turn on notifications because what we're about to discuss could become the most significant story of our generation. And here's why engagement matters. When you like and comment, it pushes this information to more people who need to see it. Knowledge shared is knowledge multiplied. So commit right now to watching until the end, because I promise you, what we reveal in the final section will challenge everything you think you know about reality itself. Let's begin with the visitor that started this entire conversation. Picture October 10th, 2025. Somewhere between Mars and Earth, hurtling through the vacuum of space, travels an object unlike anything we've encountered before. 3I/Atlas isn't just moving fast. It's traveling at velocities that shouldn't be possible for something of its estimated mass. Over 33 billion tons of material racing through our solar system. To put that in perspective, that's roughly equivalent to the weight of 100,000 Empire State Buildings, compressed into a single cosmic object, moving faster than anything natural should move at that size. The story begins months earlier on July 1st, 2025, when the Atlas telescope in Chile detected an anomaly. At first, it appeared unremarkable, just another space rock among millions. But as astronomers calculated its trajectory, they realized something stunning. This visitor came from beyond our solar system, from the unfathomable depths of interstellar space. It had traveled for potentially millions of years through the cold darkness between stars before arriving at our doorstep. But that's not the disturbing part. What makes 3I/Atlas particularly intriguing, what keeps scientists up at night analyzing data, isn't just its origin. It's the improbable series of coincidences surrounding its path through our solar system. According to calculations published by Avi Loeb's team at Harvard, the probability of 3I/Atlas naturally aligning with the orbital planes of Venus, Mars, and Jupiter is approximately 0.2%. Think about what that means. Out of all the infinite possible trajectories an interstellar object could take through our solar system, countless billions of potential paths, this one chose a route that brings it remarkably close to our major planets, following their orbital planes with uncanny precision. It's like throwing a dart blindfolded from another city and hitting not just the bullseye, but doing so while the dartboard is spinning, while you're standing on a moving platform, while the building itself is rotating. The statistical improbability is staggering. Natural objects don't behave this way. Random trajectories don't produce such elegant, precise alignments. Unless, of course, they're not random at all. The plot thickens dramatically when you examine the timing. Loeb warns that as 3I/Atlas moves behind the Sun in late October, it enters what he describes as a strategic blind spot. For several crucial weeks, our ability to observe the object becomes severely limited. The Sun's overwhelming brightness and radiation create a zone where even our most powerful telescopes cannot penetrate. And this is where conventional science meets speculative possibility, if 3I/Atlas were some form of alien technology, some kind of interstellar probe or reconnaissance vessel, this would be the perfect moment to deploy smaller craft or conduct operations without Earth-based detection. The window between November 21st and December 5th becomes particularly significant in Loeb's calculations. This represents the time frame when any theoretical deployments could reach optimal positions relative to Earth. When smaller probes, if they exist, could position themselves throughout our inner solar system without being observed. It's a narrow window, but potentially consequential enough to alter the course of human history. Now, before you dismiss this as science fiction, before you click away thinking this is just another baseless conspiracy theory, consider the evidence that has even skeptics pausing. The object's estimated mass of over 33 billion tons makes it anomalously massive for a typical comet. Comets are usually much smaller, more fragile structures. This is something different. Its acceleration patterns don't quite match what we'd expect from simple outgassing, the normal process where frozen materials sublimate and create thrust as a comet approaches the Sun's heat. The numbers don't add up. The physics doesn't align with known comet behavior. Most puzzling of all, when the Hubble Space Telescope captured images of 3I/Atlas, it revealed something completely unexpected. A teardrop-shaped cloud of dust that appeared to be leading the object rather than trailing behind it like a traditional comet tail. Comet tails always point away from the Sun, pushed by solar radiation and solar wind. They trail behind the comet nucleus like hair flowing behind someone running. But 3I/Atlas shows something different. The dust cloud precedes the object itself, suggesting forces or mechanisms we don't understand are at work. This isn't humanity's first encounter with mysterious interstellar visitors. Remember Oumuamua, that cigar-shaped object that passed through our solar system in 2017? That visitor exhibited acceleration without visible outgassing, leading to years of scientific papers, heated debates, and no definitive answers. The scientific community remains split on whether Oumuamua was a natural object, possibly a nitrogen iceberg from a distant planetary system, or something artificial. The debate never reached resolution. We simply watched it leave, carrying its secrets back into the darkness of space. Then came Borisov in 2019, which looked and acted more like a conventional comet. It had the expected tail, the expected composition, the expected behavior. Scientists breathed a sigh of relief. Perhaps Oumuamua was just an anomaly, a one-time oddity in the cosmic parade. But then 3I/Atlas arrived, and it combines elements of both previous mysteries while adding entirely new puzzles of its own. It's like the universe is gradually escalating, showing us progressively more puzzling visitors, testing our understanding, challenging our assumptions. The most recent observations from Mars orbiters have added another layer to this deepening mystery. On October 3, 2025, as 3I/Atlas passed within 30 million kilometers of Mars, both the European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter captured something intriguing. The images show the object surrounded by what appears to be an asymmetric halo, an uneven distribution of material with density variations that don't match typical cometary behavior. Natural processes create symmetry. Uniform outgassing produces uniform halos. But this shows structure, pattern, variation. Some researchers studying these images claim to see evidence of structured patterns within the dust cloud, geometric arrangements that suggest organization rather than chaos. Other scientists insist these are simply artifacts of image processing, the human brain's tendency to find patterns where none exist, the same cognitive bias that makes us see faces in clouds or hear messages in random noise. The debate grows more heated with each new image, each new data point. What really has the scientific community buzzing, what's generating countless papers and emergency peer review sessions, is the object's composition analysis from the James Webb Space Telescope. Webb revealed an unprecedented carbon dioxide to water ice ratio of 8:1, among the highest ever recorded for any comet, interstellar or otherwise. This unusual chemistry suggests 3I/Atlas formed in conditions radically different from anything in our solar system, conditions we've never observed, environments that might not even exist in nature as we understand it. Some scientists argue this supports a natural origin, that 3I/Atlas came from a distant, chemically exotic star system where planetary formation occurred under wildly different conditions than our own. Others, including members of Loeb's team, suggest such unusual composition could indicate artificial construction. A structure designed to mimic natural objects while maintaining structural integrity during millions of years of interstellar travel would need unusual materials, exotic compositions, precisely the kind of chemical signatures we're observing. The debate has become so intense, so contentious, that the SETI Institute felt compelled to publish a formal paper directly addressing the alien spacecraft hypothesis. Their analysis, while acknowledging the object's unusual characteristics, points out that extraordinary claims require extraordinary evidence. They note that the object's behavior, while unusual, falls within the range of what exotic natural phenomena might produce. We live in a strange universe. Sometimes natural processes create outcomes that appear designed. Sometimes coincidences happen. Sometimes improbable events occur simply because the universe is vast enough that even unlikely events eventually manifest. Yet even the SETI paper, even the most conservative analysis from the most skeptical scientists, admits there are aspects of 3I/Atlas that remain genuinely puzzling. Aspects that don't fit neatly into our current models of cometary behavior or interstellar object dynamics. The scientific method demands we remain open to all possibilities until evidence conclusively eliminates them. And so far, despite intense scrutiny, despite thousands of hours of observation and analysis, we haven't eliminated any possibilities. Everything remains on the table. As we speak, as you're watching this video, 3I/Atlas continues its journey through our inner solar system, currently hidden behind the sun's glare, invisible to our telescopes, moving through that strategic blind spot that has Loeb so concerned. When it emerges in early November, when it finally becomes visible again after weeks of obscurity, every major telescope on Earth and in space will be trained on it. The Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope, ground-based radio observatories, spacecraft throughout the solar system, all focused on this single object. The coming weeks could provide definitive answers to whether we're witnessing a remarkable but natural cosmic coincidence or something that rewrites our understanding of our place in the universe. Something that confirms we are not alone, that intelligent life exists beyond Earth, that we are being observed or studied or contacted. The fact that even conservative scientists, researchers who have spent careers debunking UFO claims and alien conspiracy theories, are keeping an open mind tells you everything about how unusual this situation has become. Think about the implications for just a moment. Let your mind really grasp what this could mean. If 3I/Atlas is artificial, if it's a probe or spacecraft or some form of technology created by intelligent beings, it would mean that somewhere in our galaxy, perhaps from that mysterious thick disk region of the Milky Way where scientists believe it originated, there exists a civilization capable of launching objects across interstellar distances. Not just capable of space travel within their own solar system, but capable of sending missions across the vast gulfs between stars. The trajectory calculations suggest this object has been traveling for millions, perhaps billions of years. What kind of patience would that require? What kind of long-term planning, what kind of civilizational stability, what kind of technological prowess? Human civilization has existed for maybe 10,000 years. Our space program has existed for less than 70 years. We've barely sent probes to the edge of our own solar system. The Voyager spacecraft, our most distant human-made objects, have been traveling for over 40 years and have only just recently entered interstellar space, only just left our sun's sphere of influence. But to send something across actual interstellar distances, to target another star system, to arrive at a specific destination after millions of years of travel, that requires technology, planning, and stability beyond our current comprehension. It requires a civilization that thinks in timescales of geological epochs, that builds projects knowing the results won't be seen for thousands of generations, that has transcended the short-term thinking that dominates human society. And perhaps most unsettling, perhaps the question that should keep us all awake at night, what would be the purpose of such a mission? Why send anything across interstellar space at all? Why arrive at our solar system at this precise moment in human history, when we finally have the technology to detect and study it? Is that coincidence? Or is there something about our current technological level, our recent emergence as a spacefaring species, that triggered interest or attention or action from something out there in the cosmos? The questions multiply faster than answers can be found. But while the world watches 3I/Atlas, while telescopes track its movement and scientists debate its nature, other equally profound developments are unfolding across multiple fields of human knowledge. Developments that, when viewed together, paint a picture of a species standing at a threshold, a pivotal moment when everything could change. Let me share what else is happening right now that you need to know about. While conspiracy theories and scientific debates swirl around 3I/Atlas, hard data continues pouring in from multiple space agencies, creating an increasingly detailed picture of this enigmatic visitor. Just this week, fresh observations from spacecraft stationed around Mars have provided our clearest view yet of the object. What they're revealing challenges both the alien hypothesis and our understanding of natural comets in ways nobody anticipated. The European Space Agency's latest images, captured by their ExoMars Trace Gas Orbiter on October 3rd, show 3I/Atlas as a fuzzy white dot moving against the star field. That might not sound impressive at first. You might think, why are we excited about a fuzzy dot? But consider what it took to capture these images. The cameras that photographed 3I/Atlas were designed to study the Martian surface from just a few hundred kilometers away, designed to photograph rocks and craters and geological features in high resolution. Capturing a relatively dim object 30 million kilometers distant pushed these instruments to their absolute limits, far beyond their design specifications. Nick Thomas, the principal investigator for the Cassis camera system, described it perfectly when he said it was like trying to photograph a firefly with a telescope designed to study mountains. The technical achievement alone is remarkable, but what those images revealed is even more remarkable than the feat of capturing them. What makes these observations particularly valuable is the timing. As 3I/Atlas approached Mars, it was entering what scientists call its active phase. The sun's heat had begun working on its frozen surface, warming ices that had been frozen for millions of years, causing the spectacular transformation that turns a cold, dead rock into a glowing cosmic butterfly surrounded by clouds of sublimating gas and dust. The data shows that the object's coma, that glowing envelope of gas and dust surrounding the nucleus, extends far beyond what initial models predicted. We're talking about a cloud of material that would dwarf most mountains on Earth, spreading outward in patterns that seem to pulse and shift with an almost rhythmic quality. Natural processes don't usually produce rhythms. Rhythms suggest periodicity, cycles, organization. Random outgassing creates random patterns. But 3I/Atlas shows something different. Something that repeats. Something that almost looks intentional. NASA has now integrated data from no fewer than 14 different instruments across 8 spacecraft, creating an unprecedented observation campaign tracking 3I/Atlas from multiple angles, multiple wavelengths, multiple perspectives simultaneously. The consensus emerging from this massive collaborative effort reveals an object that defies easy categorization. Yes, it's exhibiting typical cometary behavior in many ways. There's outgassing visible in certain wavelengths. There's a developing tail pointing away from the sun. Spectroscopic analysis shows signatures of common cometary molecules like water vapor, carbon dioxide, carbon monoxide. But it's also doing things we've never seen before. Things that don't fit the models. Things that make experienced comet researchers pause and reconsider assumptions they've held for entire careers. For instance, the rate of brightening as 3I/Atlas approaches the sun doesn't follow the standard curve. Most comets brighten predictably as they warm up, following well-understood mathematical relationships discovered through centuries of observation. We can predict with remarkable accuracy how bright a comet should appear at any given distance from the sun. It's basic physics. More heat equals more sublimation equals more reflected light equals more brightness. A simple, elegant relationship. But 3I/Atlas shows sudden jumps in brightness, dramatic increases that happen in hours rather than the gradual changes we expect. It's almost like something is switching on and off, like systems activating and deactivating, like controlled bursts rather than continuous outgassing. Skeptics of the alien hypothesis point out that this could be explained by uneven surface composition. Perhaps there are pockets of highly volatile materials, exotic ices that sublimate suddenly when exposed to sunlight, creating bursts of activity. But even the skeptics admit they've never seen patterns quite like this before, never seen brightness variations with this specific signature. The chemical analysis has become even more intriguing, even more puzzling with each new data set. Beyond that remarkable 8:1 carbon dioxide to water ratio that I mentioned earlier, spectrometers have now detected traces of complex organic molecules. These are carbon-based compounds, some of them quite sophisticated in structure, molecules that by all our current understanding shouldn't survive in interstellar space for the millions of years this object has supposedly been traveling. Interstellar space isn't empty. It's filled with radiation. Cosmic rays, high-energy particles, ionizing radiation that breaks chemical bonds and destroys complex molecules. It's a harsh environment, far more destructive than anything we experience on Earth. Yet 3I/Atlas carries organic molecules that appear fresh, intact, undamaged by millions of years of radiation exposure. How? Our models can't explain it. Either the object hasn't been traveling as long as we think, or it has some form of shielding that protected these molecules, or the molecules are being actively produced by some process we don't understand. These molecules, similar to those found in the most primitive meteorites in our solar system, suggest 3I/Atlas might be older than our sun itself. We could be looking at a time capsule from the early days of our galaxy, from a time when the Milky Way was young and star formation was far more active, when conditions were different than anything we see today. Material preserved in the deep freeze of interstellar space, now delivering samples from an ancient era directly to our doorstep. Recent radar observations from the Arecibo Observatory, captured before its unfortunate structural collapse, managed to bounce signals off 3I/Atlas when it was still in the outer solar system. These radar returns provide information that optical telescopes cannot, revealing details about size, shape, surface properties, rotation. The data suggests a nucleus, the solid core beneath all that gas and dust, that's surprisingly large and surprisingly smooth. Most comet nuclei are irregular, potato-shaped objects, lumpy and misshapen, formed through gradual accretion of material. They look exactly like what they are, loose collections of ice and rock held together by weak gravity. But 3I/Atlas appears almost spherical, with a reflectivity pattern that some researchers describe as too perfect to be natural. Perfect spheres don't occur naturally at this scale. Natural objects have irregularities, imperfections, asymmetries. But 3I/Atlas shows uniformity that suggests either extremely unusual formation conditions or possibly artificial construction. Of course, and this is where the scientific debate gets heated, other researchers argue that we simply haven't seen enough interstellar comets to know what natural looks like for these objects. Our sample size is 3, Oumuamua, Borisov, and now 3I/Atlas. That's an absurdly small statistical sample from which to draw conclusions. Maybe interstellar comets are just naturally smoother than solar system comets. Maybe the conditions in interstellar space, millions of years of micrometeorite impacts, somehow smooth surfaces. Maybe we're seeing something perfectly natural that we just haven't encountered before. The November timeline that has conspiracy theorists so concerned does coincide with some legitimate scientific milestones that have nothing to do with speculation. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer, will attempt observations of 3I/Atlas just after its closest approach to the Sun. This is genuinely significant because JUICE carries instruments specifically designed to analyze the chemical composition of icy bodies. These instruments can detect molecules and compounds that other spacecraft cannot, can penetrate deeper into the coma to examine the nucleus itself, can provide data we desperately need to solve this mystery. If 3I/Atlas is going to reveal its secrets, if there are definitive answers to be found, this might be our best shot at uncovering them. The window is narrow. The object is moving fast. If we miss this opportunity, we might never get another chance. Once 3I/Atlas leaves our solar system, once it accelerates back into the darkness of interstellar space, it's gone forever. We'll never see it again. Whatever questions remain unanswered will likely stay unanswered for the rest of human history. Meanwhile, ground-based observatories are preparing for what they're calling the viewing window of the century. When 3I/Atlas emerges from behind the Sun in early November, it will be perfectly positioned for observation from the southern hemisphere. The Very Large Telescope in Chile, the most powerful optical telescope array on Earth, has cleared its schedule for continuous monitoring. They've canceled other projects, delayed other observations, dedicated their most advanced instruments to tracking this single object. They're planning to use a technique called interferometry, combining light from multiple telescopes to achieve resolution that could theoretically detect features as small as a few meters across on the comet's surface. If the conditions are right, if the atmosphere cooperates, if everything aligns perfectly, we might be able to see surface details, to examine the nucleus directly, to determine once and for all whether we're looking at a natural object or something constructed. The scientific community is also closely watching for what doesn't happen. This is crucial. If 3I/Atlas is truly just a natural comet, albeit an unusual one, it should begin to fade predictably after perihelion, after its closest approach to the Sun. Its trajectory should remain stable, following the laws of orbital mechanics without any unexplained course corrections. Natural objects obey Newton's laws. They follow predictable paths determined by gravity alone. Any deviation from these predictions, any acceleration that can't be explained by outgassing, any course change that seems intentional, would immediately elevate this from an interesting astronomical event to something potentially paradigm-shifting. One detail that hasn't received much attention outside scientific circles, one piece of data that most people aren't aware of, is the object's rotation. 3I/Atlas appears to be tumbling in a complex pattern that suggests it's experiencing forces beyond simple solar radiation pressure. Most space rocks rotate around a single axis, spinning like a top. But 3I/Atlas is rotating on 3 axes simultaneously, tumbling through space in a complex dance that creates a pattern repeating every 17.3 hours. That's oddly specific for a supposedly random celestial body. Natural objects don't usually tumble in such precise patterns. Random collisions, random forces create random rotations. But this shows periodicity, precision, repeatability. Some scientists propose this could be due to asymmetric outgassing, jets of vapor shooting out unevenly and causing the object to spin in complex ways. But the rotation pattern's mathematical elegance, its precise periodicity, troubles some researchers. It looks almost engineered. The latest models from NASA's Jet Propulsion Laboratory, the gold standard for trajectory calculations, suggest that 3I/Atlas's path through our solar system isn't quite as improbable as initially thought. When you account for gravitational perturbations from galactic tides over millions of years, when you consider the complex gravitational environment the object has passed through during its long journey, the chances of an interstellar object following this particular trajectory increase from 0.2% to about 1.8%. Still unlikely, still improbable, but not impossibly so. Not so unlikely that it demands exotic explanations. Sometimes unlikely things happen. The universe is vast enough that even improbable events eventually occur somewhere, somewhen. Yet this same modeling, these same sophisticated calculations, reveals something else interesting, something that brings us right back to the mystery. The object appears to have undergone a slight course correction sometime in the last few thousand years before entering our solar system. A small change in trajectory, barely detectable, but statistically significant. The natural explanation? A close encounter with an unseen massive object, perhaps a rogue planet or brown dwarf that diverted its path slightly. The alternative explanation? Well, that's where imagination and scientific speculation merge into something unsettling. What keeps even skeptical scientists engaged, what prevents this from being dismissed entirely, is the sheer number of anomalies. Any single oddity could be explained away. Unusual composition, exotic formation environment, strange rotation, asymmetric outgassing, unexpected trajectory, gravitational perturbation. Each individual mystery has potential natural explanations. But 3I/Atlas presents a constellation of mysteries, a convergence of anomalies. It's too massive, too smooth, too precisely rotating, too chemically exotic, and following too convenient a path. As one researcher put it to me off the record, someone who requested anonymity because even discussing this publicly could harm their career, if you were trying to design an object that would make scientists question everything while still maintaining plausible deniability as a natural phenomenon, you couldn't do much better than 3I/Atlas. It sits right at the boundary between possible and impossible, natural and artificial. It's almost like it's designed to provoke exactly the debate we're having. The next few weeks will be crucial. Perhaps the most important weeks in the history of astronomy, the history of human scientific endeavor. As 3I/Atlas swings around the sun and begins its outbound journey, we'll have our best opportunity to solve these mysteries. Every major space agency has instruments ready. Every major telescope has time allocated. Thousands of scientists worldwide are waiting, analyzing, debating. If it's going to surprise us, if there's any truth to the more exotic theories, we should know soon. The universe rarely gives us such clear deadlines for discovery. Usually, science progresses gradually, incrementally, through patient accumulation of evidence over decades or centuries. But with 3I/Atlas, we have a deadline. November 21st through December 5th. The window when everything could change. The time frame when, if Loeb is right, if the most speculative theories prove correct, we might witness something that transforms human civilization forever. Mark those dates. Remember them, because if something extraordinary is going to happen, it will happen then. But here's what's remarkable. While the world watches 3I/Atlas, while debates rage about its nature and origin, an equally profound revolution is unfolding in another domain entirely. Something is happening in space exploration, in our understanding of the cosmos, that makes the timing of 3I/Atlas's arrival seem almost prophetic. As 3I/Atlas continues its mysterious journey through our solar system, another cosmic milestone has quietly revolutionized our understanding of the universe's possibilities. Last month, NASA confirmed that humanity has now discovered 6,000 planets orbiting other stars. 6,000 worlds, each potentially as complex and varied as our own solar system. Each one a complete planetary system with its own history, its own characteristics, its own possibilities. And buried in that announcement, mentioned almost casually in the technical papers, was a detail that should make everyone pause and really think about what we're learning. At least 47 of these planets sit in what scientists call the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. Liquid water, the essential ingredient for life as we know it. The 6,000th planet itself wasn't particularly remarkable from a scientific standpoint. It's a hot Jupiter-type world, a massive gas giant orbiting a star 400 light-years away. Far too hot to harbor life, far too massive to have a solid surface. But what it represents is absolutely staggering. Think about this timeline. 30 years ago, we knew of exactly 0 planets outside our solar system. 0. We had theories, we had strong reasons to believe other planets existed, but we had no proof. The first confirmed exoplanet around a sun-like star, 51 Pegasi b, was discovered in 1995. Just 30 years ago. Now we're finding them so fast, at such an accelerating rate, that individual discoveries barely make the news unless they're especially weird, especially Earth-like, or especially close. We've gone from wondering whether any planets exist elsewhere to cataloging thousands of them, to beginning to understand the amazing diversity of worlds our galaxy contains. And believe me, some of them are spectacularly weird. Planets so strange, so beyond our imagination, that science fiction writers couldn't have invented them if they tried. Take WASP 76b, for example. This is a planet where it literally rains liquid iron. Let that sink in for a moment. Not water, not methane or ammonia or any liquid we associate with weather. Iron. Molten metal falling from alien skies. The day side of this tidally locked world, the hemisphere permanently facing its star, reaches temperatures of 4,300 degrees Fahrenheit. That's hot enough to vaporize metal, to turn solid iron into gas that rises into the atmosphere. Then powerful winds, screaming at thousands of miles per hour, carry that iron vapor to the cooler night side where it condenses and falls as metallic rain. Picture standing on the Terminator, the boundary between day and night, watching a storm of liquid iron droplets falling from the sky, each drop glowing orange-hot as it descends. It's not just alien. It's almost incomprehensible. Or consider 55 Cancri e, discovered just this year, a super-Earth covered in oceans of lava with clouds that might be made of vaporized rock. The entire surface is molten. There's no solid ground anywhere. Just endless seas of liquid stone at temperatures that would instantly vaporize anything we could build, circling a star so close that its year lasts just 18 hours. In less than a day, this planet completes a full orbit. These aren't science fiction concepts anymore. They're not imaginative speculation or artistic license. They're real places that exist right now, at this very moment, orbiting distant stars in our galaxy. You could, theoretically, point a telescope at these stars and observe these planets. They're real. They exist. And they're teaching us that the universe is far stranger, far more diverse than we ever imagined. But the truly exciting developments, the discoveries that keep astrobiologists awake at night with excitement, are happening with the smaller, rockier planets. The ones that might actually harbor life. The ones that could have oceans, atmospheres, even ecosystems. The TESS mission, the Transiting Exoplanet Survey Satellite, has been particularly successful at finding these Earth-sized worlds. Unlike the Kepler mission, which stared at one small patch of sky for years, TESS scans almost the entire sky, focusing particularly on stars closer to Earth. This is crucial because proximity means these planets are much easier to study with follow-up observations. We can point our most powerful telescopes at them, analyze their atmospheres, search for signs of life. Just last week, researchers announced the discovery of LP 890-9b, a super-Earth just 22 light-years away. In cosmic terms, that's practically next door. It's in our immediate neighborhood. And what's remarkable about this planet isn't just its size, roughly 1.5 times Earth's radius, or its proximity. It's the fact that it's orbiting in the habitable zone of a red dwarf star. This matters tremendously. Red dwarfs make up 75% of all stars in our galaxy. 3 out of every 4 stars you see in the night sky are red dwarfs, small, cool, incredibly long-lived stars that burn their fuel so slowly they could shine for trillions of years. Our sun will die in about 5 billion years. Red dwarfs could still be shining when the universe is 100 times older than it is now. So if planets around red dwarf stars can support life, if those compact habitable zones can harbor living worlds, the universe might be teeming with it. Billions upon billions of potentially habitable worlds, circling the most common stars in existence, all of them potentially developing their own biospheres, their own evolutionary paths, possibly their own civilizations. The James Webb Space Telescope has already begun analyzing LP 890-9b's atmosphere, or attempting to. It's at the edge of what's currently possible, but Webb's instruments are looking for biosignatures, the chemical fingerprints of life. Certain combinations of gases in an atmosphere are difficult to explain without biological processes. Oxygen and methane together, for instance, react with each other quickly. To maintain both gases in an atmosphere simultaneously requires constant replenishment. On Earth, that replenishment comes from life. Plants produce oxygen. Bacteria produce methane. If we find both together in the atmosphere of a distant planet, it's a strong hint that something might be alive there. Speaking of Webb, this remarkable space telescope has completely transformed our ability to study exoplanet atmospheres. We're now detecting molecules we never thought we'd be able to see from Earth, let alone analyze in detail. Water vapor, methane, carbon dioxide, even clouds and hazes at specific altitudes. On K2-18b, a planet 8.6 times the mass of Earth orbiting a red dwarf 120 light-years away, Webb detected something extraordinary that sent waves of excitement through the astrobiology community. Dimethyl sulfide, a molecule that, on Earth, is only produced by living organisms, specifically marine phytoplankton. The tiny microorganisms that form the base of our ocean food web, that produce much of the oxygen we breathe, that support entire ecosystems. There is no known non-biological process on Earth that produces dimethyl sulfide in significant quantities. Now, before you get too excited, before you start thinking we've found definitive proof of alien life, scientists are cautious. There might be non-biological ways to produce this molecule that we don't know about yet, chemical processes that don't occur on Earth, exotic reactions in alien atmospheres with different temperatures and pressures and compositions. The universe is creative. Chemistry under alien conditions might produce unexpected results. But it's exactly the kind of discovery that makes scientists' hearts race, that makes them cancel meetings and stay up late analyzing data and running models. It's a tantalizing hint, possibility, a maybe, and in the search for life beyond Earth, maybes are precious. The variety of planetary systems we're discovering is forcing us to completely rewrite our theories of planet formation. Our solar system, The orderly arrangement of small rocky planets close to the Sun and large gas giants farther out turns out to be just one possibility among countless configurations. We've found hot Jupiters, massive gas giants orbiting closer to their stars than Mercury is to our Sun, completing orbits in days or even hours. These shouldn't exist according to our original models. Gas giants form far from their stars where it's cold enough for ice to exist. Yet here they are, scorching worlds whipping around their stars at incredible speeds. They must have migrated inward, either through gravitational interactions with other planets or through friction with the protoplanetary disk. Planet formation is dynamic, chaotic, far more complex than we realized. We found super-Earths and mini-Neptunes, entire categories of planets that don't exist in our solar system. Super-Earths are rocky worlds larger than Earth but smaller than Neptune, potentially with deep oceans and thick atmospheres. Mini-Neptunes are smaller versions of ice giants, with significant hydrogen-helium atmospheres surrounding possible rocky cores. These planet types appear to be extremely common. More common, in fact, than Earth-sized planets. Our solar system is missing a whole class of planets that most other systems possess. We've found planets orbiting binary stars, real-world Tatooines with twin suns in their skies. We've found planets around pulsars, orbiting the dense corpses of dead stars in lethal radiation baths. We've even found rogue planets, worlds that don't orbit any star at all but drift alone through the darkness of interstellar space, wandering the galaxy as cosmic nomads. Some of these rogue planets might retain enough internal heat to support subsurface oceans, to potentially harbor life that never sees a sun. One of the most intriguing recent discoveries, one that captured public imagination despite being several years old now, is the TRAPPIST-1 system. 7 Earth-sized planets orbiting a single ultra-cool red dwarf star just 39 light-years away. 7 planets, all rocky, all similar in size to Earth, and 3 of them sitting squarely in the habitable zone where liquid water could exist. What makes this system extraordinary is how compact it is. All 7 planets orbit so close together that if you stood on one, the others would appear larger in the sky than our moon appears from Earth. You could see neighboring planets as disks, visible to the naked eye, showing phases like Venus does from Earth. The entire system would fit comfortably inside the orbit of Mercury. Yet it might contain 3 potentially habitable worlds, 3 chances for life to arise in a single system. Imagine the implications if life evolved on multiple planets in the same system. Would they develop independently, following separate evolutionary paths? Or would meteorite impacts spread life between them in a process called panspermia, seeding multiple worlds with the same basic biochemistry? If civilizations arose on multiple planets in this system, they could potentially detect each other with technology no more advanced than what we possess now. They could communicate across interplanetary distances with powerful radio transmitters. They might even visit each other, building spacecraft to bridge gaps of just a few million kilometers. The search isn't just about finding any planets anymore. The paradigm has shifted. We've confirmed that planets are common. Now we're searching for the right planets. Earth-like worlds in habitable zones with the right characteristics to potentially support life. And we're developing the technology to examine them in unprecedented detail. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct a comprehensive census of exoplanets using a technique called gravitational microlensing. This method can detect planets that other techniques miss, including Earth-mass planets orbiting at Earth-like distances from their stars, planets too far from their stars to be detected by the transit method, planets around stars too faint for radial velocity measurements. Roman is expected to find thousands of new exoplanets, potentially including some that are almost exact twins of Earth. Same size, same orbital distance, same star type. We might discover a planet so similar to Earth that we could reasonably speculate about continents and oceans, weather patterns and seasons, day and night cycles almost identical to our own. But here's where things get really interesting, where statistics and probability create implications that are almost overwhelming. Statistical analysis of the planets we've found so far suggests that Earth-sized planets in habitable zones aren't rare at all. They're not special. They're not even uncommon. In fact, they might be extraordinarily common among the most typical planetary configurations the universe produces. Conservative estimates, the most cautious calculations that assume life requires very specific conditions, suggest there could be at least 300 million potentially habitable planets in our galaxy alone. 300 million worlds where liquid water might exist, where temperatures might allow complex chemistry, where life might arise. That's conservative. The low estimate. Some researchers put the number much higher. When you relax the requirements slightly, when you consider that life might be more adaptable than we assume, when you account for moons around gas giants and deep ocean worlds covered in ice, the number of potentially habitable environments in our galaxy could exceed 1 billion. 1 billion places where life might exist right now. And that's just in the Milky Way. Our galaxy is large but not unique. The observable universe contains approximately 2 trillion galaxies. 2 trillion island universes, each containing hundreds of billions of stars, each of those stars potentially hosting multiple planets. Do the math. Really think about the numbers. Even using the conservative estimate of 300 million habitable planets per galaxy, multiplied by 2 trillion galaxies, we're talking about 600 quintillion potentially habitable worlds in the observable universe. That's a 6 followed by 20 zeros. More potentially habitable planets than there are grains of sand on every beach on Earth. The numbers become incomprehensible. They break our capacity to understand scale. We can write them, but we can't truly grasp them. Somewhere in that incomprehensible vastness, life almost certainly exists. The probability approaches certainty when the numbers get this large. Yet despite these staggering numbers, despite the statistical near-certainty that we're not alone, we haven't found any definitive signs of life. No unambiguous biosignatures in exoplanet atmospheres. No detected radio signals that can only be explained by technological civilization. No spacecraft visiting our solar system that we can prove are artificial. This is the heart of the Fermi paradox, the troubling question that physicist Enrico Fermi posed decades ago. Where's everybody? If life is common, if the universe is teeming with potentially habitable worlds, why haven't we detected anyone? Why do we appear to be alone? Some scientists argue we're looking in the wrong places or with the wrong methods. Perhaps life is common but technological civilization is rare. Perhaps intelligent species don't survive long enough to become detectable, destroying themselves through war or environmental catastrophe or resource depletion. Perhaps they deliberately hide, avoiding detection for reasons we can't understand. Others suggest life might be common, but intelligent life, civilization-building species capable of technology and science, might be vanishingly rare. Perhaps Earth represents an improbable confluence of favorable conditions. Perhaps the path from simple life to complex intelligence requires so many unlikely steps that it almost never completes. Or perhaps, and this brings us back to 3I/Atlas, back to the mysterious visitor currently hidden behind our sun, perhaps they're already here and we're just beginning to recognize the signs. Perhaps contact doesn't look like what we expected. Perhaps we've been naive about what interstellar exploration would actually entail, about how advanced civilizations would actually behave. The timing feels significant, noteworthy, almost suspicious. Just as we're developing the technology to detect and study other worlds, just as we're realizing how common potentially habitable planets are, just as we're beginning to seriously search for life beyond Earth, we receive our third interstellar visitor in just 8 years. 3 objects entering our solar system from interstellar space in less than a decade, after all of human history passed without us detecting any. Is this coincidence? Statistical fluctuation? Or is there something about reaching this level of technological sophistication, about becoming a species capable of detecting exoplanets and searching for biosignatures and contemplating our place in the cosmic community, that attracts attention? Some researchers have suggested that our radio emissions, which have been leaking into space for over a century now, spreading outward in an expanding sphere at the speed of light, might act as a beacon. Any civilization within 100 light-years with sufficiently advanced detection equipment could detect Earth's radio transmissions. They would know immediately and unambiguously that technological civilization exists here. Earth would appear as an unusually radio-bright planet, producing emissions in frequencies that natural processes rarely generate. It would be obvious, unmistakable, a clear signature of technology, of intelligence, of a species that has mastered electromagnetic radiation. The next decade promises even more revolutionary discoveries in this field. The Habitable Worlds Observatory, still in early planning stages but with strong support from NASA and the scientific community, would be specifically designed to image Earth-like exoplanets directly. Not just detect them through transits or radial velocity, but actually photograph them, resolve them into visible disks, analyze their atmospheres with unprecedented precision. The European Extremely Large Telescope, currently under construction in Chile, will have a mirror 39 meters in diameter. That's larger than most buildings. With that enormous light-collecting area and cutting-edge adaptive optics to compensate for atmospheric distortion, it might have sufficient resolution to potentially see continents on nearby exoplanets, to distinguish large oceans from land masses, to detect seasonal changes in vegetation if it exists. We might actually be able to map alien worlds, create atlases of planets we've never visited, will never visit in our lifetimes, planets dozens or hundreds of light-years distant. We might even detect the lights of alien cities if they exist, if intelligent species have developed similar technology, if they illuminate their nights with artificial light the way we do. Think about that possibility for a moment. Really let it sink in. Within your lifetime, probably within the next 20 years, we might not just know that life exists elsewhere in the universe. We might be able to see it, watch alien weather patterns develop in real time, observe seasonal changes on distant worlds, track cloud formations, measure atmospheric composition, perhaps even detect artificial structures if a civilization has built on a large enough scale. The 6,000 planets we've discovered so far are just the beginning. A tiny fraction. Conservative estimates suggest our galaxy contains at least 100 billion planets. We've examined 0.006% of them. Not even 1/100th of 1%. It's like judging all of Earth's biodiversity by looking at a single drop of ocean water and declaring we understand all life on the planet. What wonders are still out there waiting to be discovered? What impossible worlds orbit distant stars? What exotic chemistries support alien ecosystems? What forms does life take when evolution proceeds under conditions radically different from Earth? And perhaps most tantalizingly, the question that drives so much of this research, the question that motivates billion-dollar missions and consumes entire careers. On how many of them is someone looking back at us, wondering if they're alone? If you're still watching, if this deep dive into the mysteries unfolding around us has captured your attention, I need you to do something right now. Hit that like button if you haven't already. This tells the algorithm that this content matters, that people want to understand what's really happening beyond the surface-level news coverage. Drop a comment below telling me what aspect of this story fascinates you most. Is it 3I/Atlas and the possibility of an interstellar probe? Is it the discovery that potentially habitable worlds might number in the billions? Is it something else we're about to discuss? Your engagement literally shapes what happens next. YouTube's algorithm doesn't care about quality or truth or importance. It cares about engagement. When you like, comment, and share, you're not just supporting this channel. You're ensuring this information reaches more people who need to see it. You're fighting against the tendency of social media to bury complex, nuanced content in favor of sensationalism and clickbait. So comment. Tell me where you're watching from. Tell me what time it is there. Tell me whether you think 3i/Atlas is natural or artificial. Engage with this content and with each other. Build community around understanding rather than speculation. That's how we collectively navigate the extraordinary moment in history we're living through. And we're only halfway through what I need to share with you today. The next sections cover developments that, when viewed alongside 3i/Atlas and the exoplanet revolution, paint a picture of a species standing at a threshold. A moment when everything might be about to change. Let's talk about quantum computing, because this technology is about to transform everything. 2025 will be remembered as the year quantum computing stopped being a promise and started being a reality. The United Nations didn't randomly declare this 2025 as the International Year of Quantum Science and Technology by accident. They recognized that we're witnessing a fundamental shift in human capability, a transition as significant as the invention of the transistor or the development of the Internet. The implications are staggering, touching every aspect of human civilization from medicine to materials science, from artificial intelligence to cryptography. Google's Willow quantum processor achieved something that seemed impossible just months ago. It solved a computational problem in 5 minutes that would take the world's most powerful classical supercomputers longer than the age of the universe to complete. Not years, not centuries, longer than the 13.8 billion years the universe has existed. That's not an incremental improvement. That's a fundamental leap into capabilities that redefine what's computationally possible. What makes this achievement particularly significant isn't just the raw computational power, though that alone is remarkable. It's that Willow demonstrated something called quantum error correction at scale. This has been the holy grail of quantum computing, the obstacle that has prevented these machines from being practical despite decades of research. Quantum bits, or qubits, are notoriously fragile. They exist in superposition, simultaneously representing multiple states, but the slightest environmental disturbance causes them to collapse into classical states, destroying the quantum advantage. Every quantum computer built before Willow faced the same fundamental problem. The more qubits you added, the more errors accumulated, until the system became useless. It was like trying to build a house where each additional brick made the entire structure more likely to collapse. You couldn't scale up. You couldn't build larger, more powerful quantum computers because adding qubits made the system less reliable, not more. Willow changed that equation completely. Google's team demonstrated that they could add more qubits while actually reducing the error rate. The system became more stable and more reliable as it grew larger. That's the breakthrough that transforms quantum computing from a laboratory curiosity into a practical technology that could reshape civilization. Once you can scale reliably, once you can build progressively larger quantum computers without losing stability, there's no theoretical limit to what becomes computationally possible. The implications ripple across every field of human knowledge. Drug discovery, currently a process that takes years or decades and costs billions of dollars, could be revolutionized. Quantum computers can simulate molecular interactions with perfect accuracy, modeling how potential drug compounds will interact with specific proteins or cellular mechanisms. Instead of synthesizing thousands of compounds and testing each one in laboratories, researchers could test millions of virtual compounds in simulations, identifying the most promising candidates before ever mixing chemicals in a beaker. This isn't speculation. It's already beginning. Pharmaceutical companies are partnering with quantum computing firms to redesign drug discovery from the ground up. Diseases that have resisted treatment, Conditions where we haven't found effective therapies despite decades of research might finally yield to drugs designed with quantum precision. Cancer treatments tailored to individual tumor genetics. Alzheimer's medications that actually halt neurodegeneration. Antibiotics that bacteria cannot develop resistance against. Materials science faces similar transformation. Every material we use, every alloy, every polymer, every ceramic, represents a specific arrangement of atoms with specific properties. Discovering new materials currently relies heavily on trial and error, on intuition developed through decades of experience, on expensive experiments that might produce nothing useful. Quantum computers can simulate material properties before anything is manufactured, predicting strength, conductivity, heat resistance, flexibility, any physical property we care about. Imagine designing batteries from first principles, simulating every possible combination of materials until you find configurations that store 10 times more energy than current lithium-ion technology. Electric vehicles with 1,000-mile ranges. Grid-scale energy storage that makes renewable energy fully practical. Portable electronics that charge in seconds and run for weeks. These aren't fantasies. They're engineering problems that quantum computers should be able to solve. Climate modeling represents another domain where quantum computing could prove transformative. Current climate models, running on classical supercomputers, can simulate global weather patterns and climate trends, but they must make simplifying assumptions. The atmosphere is too complex, with too many interacting variables, for even our most powerful computers to model every process at full resolution. Quantum computers could potentially simulate climate systems at molecular resolution, accounting for every relevant interaction, producing forecasts with unprecedented accuracy. Better climate models mean better predictions about which regions will face droughts, floods, heat waves, storms. Better predictions enable better preparation, better infrastructure planning, better resource allocation. In a world facing accelerating climate change, the ability to accurately predict regional impacts years or decades in advance could save millions of lives and trillions of dollars in prevented damage. But quantum computing also poses existential risks, particularly to cybersecurity. Most modern encryption, the systems that protect banking, communications, government secrets, military operations, relies on mathematical problems that are easy to create but extremely difficult to solve. Factoring large numbers, for instance, is computationally intensive. An encryption key might take classical computers thousands of years to crack through brute force. That's why we trust these systems. That's why sensitive information can be transmitted over public networks. Quantum computers destroy that assumption completely. Algorithms like Shor's algorithm, specifically designed for quantum computers, can factor large numbers exponentially faster than any classical method. A sufficiently large quantum computer could break RSA encryption instantly, could decrypt communications that were supposed to remain secret for decades, could compromise every system that relies on current cryptographic standards. The implications are sobering. Every encrypted message ever sent could potentially be decrypted. Every secure communication, every classified document transmitted digitally, every financial transaction, every private conversation conducted electronically, could be retroactively exposed. Intelligence agencies around the world are reportedly already harvesting encrypted communications, storing them in vast databases, waiting for quantum computers powerful enough to decrypt them. They can't read these messages now, but they're betting they'll be able to in the future. This has sparked a race to develop quantum-resistant encryption, new cryptographic systems based on mathematical problems that remain difficult even for quantum computers. The National Institute of Standards and Technology has already begun standardizing post-quantum cryptographic algorithms, preparing for a world where quantum computers are widespread. But transitioning the entire global digital infrastructure to new encryption standards represents a monumental undertaking that will take years or decades to complete. China has reportedly achieved significant advances in quantum communication, launching satellites and building quantum networks that are theoretically immune to eavesdropping. Quantum key distribution uses the laws of quantum mechanics themselves to detect any attempt at interception, making perfectly secure communication physically possible. If China successfully deploys quantum communication networks before other nations, they would possess a communication system that cannot be intercepted or decrypted, providing enormous strategic advantages. The technological race feels increasingly urgent. Quantum computing, artificial intelligence, advanced materials, biotechnology, all progressing simultaneously, all potentially providing decisive advantages to whoever achieves breakthroughs first. It's becoming clear that the next few decades will determine which nations, which civilizations, which systems of governance will dominate the remainder of human history. But here's where things connect back to our central mystery, back to 3I/Atlas and the possibility of extraterrestrial intelligence. Any civilization capable of interstellar travel, capable of sending objects across the vast distances between stars, would necessarily have mastered technologies far beyond our current understanding. Quantum computing would be primitive to them, ancient history, the equivalent of us looking back at abacuses or mechanical calculators. What could a truly advanced civilization compute? What problems could they solve that remain beyond our comprehension? Could they simulate entire universes, model every particle interaction, predict the evolution of galaxies, design stable wormholes, manipulate spacetime itself? The gap between our current capabilities and what becomes possible with mature quantum technology might be minuscule compared to the gap between us and a civilization millions of years more advanced. If 3I/Atlas is artificial, if it represents technology from such a civilization, we might be looking at engineering that makes our most advanced quantum computers seem as primitive as stone tools. We might be observing material science that allows solid objects to survive millions of years of interstellar travel without degradation. We might be seeing propulsion systems that don't just react against expelled mass but manipulate fundamental forces we don't understand. The universe might be filled with civilizations operating on principles of physics we haven't discovered yet, using technologies we can't even imagine, solving problems we don't know exist. And we're just now, in 2025, achieving quantum error correction, taking our first stumbling steps toward computational capabilities that might, eventually, allow us to begin understanding what's actually possible. The humility is overwhelming. We've been technological for barely a century, radio for 130 years, spaceflight for 68 years, quantum computing for less than a decade of practical development. If someone had described today's technology to people in 1900, they would have dismissed it as magic, as impossible, as fantasy. What will technology look like in 2100? In 2500? In 10,000 years if we survive and continue advancing? And if there are civilizations out there with that much of a head start, civilizations that began developing science and technology when Earth was still inhabited by dinosaurs or earlier, what have they become? What can they do? What would their artifacts look like? How would we even recognize them? These questions used to be purely philosophical, entertaining thought experiments without practical implications. But in 2025, with 3I/Atlas moving through our solar system, with quantum computers achieving revolutionary breakthroughs, with exoplanet discoveries confirming that potentially habitable worlds number in the billions, these questions are becoming urgent and immediate. We might need answers soon. Let me tell you about another breakthrough that's happening right now, another development that suggests we're living through a unique moment in human history. In laboratories in France, scientists achieved something that seemed impossible just years ago. They sustained fusion plasma, the superheated state where atomic nuclei fuse together and release enormous energy, for 22 consecutive minutes. 22 minutes doesn't sound impressive until you understand what it means, what it represents, what it makes possible. Fusion is the power source of stars, the reaction that makes the sun shine, that generates the light and warmth that makes life on Earth possible. For decades, scientists have been trying to recreate this process on Earth, to build reactors that generate energy through fusion rather than fission, to unlock essentially unlimited clean energy. The promise has always been tantalizing. Fusion fuel is abundant, cheap, and safe. The reaction produces no long-lived radioactive waste, no greenhouse gases, no pollution. It's the ultimate energy source, the solution to climate change and energy scarcity. But it's been perpetually just out of reach, always 20 years away no matter when you ask. The engineering challenges are immense. You need to heat plasma to temperatures exceeding 100 million degrees Celsius, 10 times hotter than the core of the sun. At those temperatures, no material can contain the plasma. Everything would instantly vaporize. So fusion reactors use magnetic fields to suspend the plasma, to keep it from touching the reactor walls, to confine and compress it until fusion reactions occur. Maintaining these conditions for even seconds requires extraordinary precision. The plasma is inherently unstable, constantly trying to escape magnetic confinement, constantly cooling, constantly requiring enormous energy input just to maintain. For fusion to be practical, to generate more energy than it consumes, you need to sustain these conditions long enough for fusion reactions to release more energy than the magnets and heating systems use. That's why 22 minutes matters. That's sustained operation, stable plasma, controlled fusion running continuously for long enough to be practically useful. It's not a laboratory curiosity anymore. It's an engineering milestone that demonstrates fusion power is achievable, that we're approaching the threshold where fusion reactors become viable energy sources. The West for tokamak in China achieved this breakthrough, using advanced superconducting magnets and new plasma control techniques to maintain stability far longer than previous attempts. They're targeting an hour of sustained operation by 2026, and continuous operation, plasma that runs indefinitely like a conventional power plant by 2030. If they succeed, if fusion power becomes practical in the next 5 to 10 years, it would transform human civilization more profoundly than perhaps any technology since fire. Imagine energy too cheap to meter, so abundant that cost becomes irrelevant. Imagine every nation having access to unlimited clean power, no dependence on fossil fuels, no strategic resource competition, no geopolitical conflicts over oil or natural gas. Imagine desalination plants powered by fusion providing unlimited fresh water to any coastal region. Imagine indoor vertical farms growing food year-round using artificial sunlight, making agriculture independent of climate and weather. Imagine direct carbon capture from the atmosphere, machines that pull CO2 directly from the air and convert it into useful products or sequester it permanently. Right now, this is impractical because it requires too much energy. But with fusion power, with energy so cheap it's essentially free, atmospheric carbon capture becomes viable. We could potentially reverse climate change, actively removing greenhouse gases faster than we emit them, restoring atmospheric composition to pre-industrial levels. Space exploration would be revolutionized. Current spacecraft are severely energy limited. Solar panels work near Earth but become less effective farther from the sun. Radioisotope thermoelectric generators, the plutonium-powered batteries that enable deep space missions, are expensive, limited in power output, and require materials that are difficult and dangerous to produce. Fusion reactors could power spacecraft with effectively unlimited energy, enabling constant acceleration, dramatically shortening travel times to distant planets, making crewed missions to Jupiter or Saturn feasible. Some fusion rocket designs could theoretically accelerate continuously for months, reaching velocities that would allow travel to Mars in weeks instead of months, to the outer solar system in months instead of years. We could establish permanent bases throughout the solar system, could mine asteroids for resources, could build orbital habitats supporting millions of people, could begin transforming humanity into a truly spacefaring civilization. and perhaps most relevant to our central mystery, perhaps most connected to questions about 3I/Atlas and extraterrestrial intelligence, fusion represents the kind of breakthrough that marks a civilization's transition to Type 1 status on the Kardashev scale, the classification system for technological civilizations based on energy usage. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 can harness all the energy output of its star. A Type 3 can harness the energy of its entire galaxy. We're currently a Type 0.7 civilization, not even Type 1 yet, still dependent on fossil fuels, still unable to control our own planet's climate or tap into the full energy potential available to us. Fusion power moves us decisively toward Type 1 status. It gives us essentially unlimited energy within our planetary system, the foundation for everything else, the capability that enables all other advanced technologies. Any interstellar civilization, any species capable of sending objects between stars, would necessarily be at least Type 2 harnessing star-scale energy. The engineering required for interstellar travel demands energy on scales we can barely imagine. If 3I/Atlas is artificial, its creators have access to power generation capabilities so far beyond fusion that the comparison might be meaningless. They might harvest energy directly from stellar cores, might extract energy from black holes through Penrose processes, might tap into dark energy or zero-point fields or physical principles we haven't discovered. The gap between our current capabilities and what mature fusion power enables might be tiny compared to the gap between fusion and what interstellar civilizations command. Yet we're taking those first steps now in 2025, achieving the breakthroughs that could, within our lifetimes, transform us into a Type 1 civilization. The timing feels significant. We're developing exoplanet detection capabilities, quantum computers, fusion power, all simultaneously, all converging in this narrow window of history. Are we being watched? Are we being evaluated? Is there something about crossing these technological thresholds that attracts attention? Before we continue, I need to ask you something. Are you still with me? Have you made it this far through this deep investigation into the converging mysteries and breakthroughs of 2025? If you have, you're exactly the kind of person who should be subscribed to this channel. Hit that subscribe button right now. Turn on notifications. This is the kind of comprehensive, detailed analysis you won't find anywhere else, the kind of content that connects dots others don't even see. And if you're still watching, if you've invested this much time in understanding what's really happening in our world right now, leave a comment. Tell me you're still here. Tell me what's resonating most with you. Are you fascinated by 3I/Atlas? Excited about fusion energy? Amazed by quantum computing? Drop a comment and let me know. Your engagement determines what content I create next, what mysteries I investigate, what stories I tell. We're building something here, a community of people who want to understand rather than just consume, who value depth over clickbait, who recognize that we're living through an extraordinary moment that demands attention and analysis. Be part of that community. Engage. Connect. Think deeply about what all of this means. Because what I'm about to share next connects everything we've discussed so far into a pattern that's both fascinating and unsettling. While fusion reactors are bringing us closer to unlimited energy and quantum computers are revolutionizing our computational capabilities, another scientific breakthrough has emerged that challenges our understanding of aging and mortality itself. And the implications, when you really think them through, are staggering beyond measure. Researchers at Stanford University successfully reversed aging in mouse brains, restoring cognitive function in elderly mice to levels comparable to young adults. This isn't about slowing aging or reducing symptoms. This is about actually reversing the damage, turning back the biological clock, making old tissue young again. The treatment extended the lifespan of these mice by 30%, equivalent to giving a human decades of additional healthy life. The mechanism is elegant in its simplicity yet revolutionary in its implications. As organisms age, our cellular repair systems become less efficient. Damage accumulates. DNA develops errors. Proteins misfold. Cellular structures degrade. Eventually, accumulated damage reaches levels incompatible with continued life. We age because our cells lose the ability to maintain themselves, to repair damage as quickly as it occurs. But what if that process could be reversed? What if you could restore cellular repair mechanisms to youthful efficiency? The Stanford team identified specific molecular pathways that control cellular maintenance and repair. By activating these pathways in aged mice, they essentially rebooted the cellular repair systems, allowing old cells to clean up accumulated damage, to repair degraded structures, to restore function. The treated mice didn't just live longer. They remained cognitively sharp, physically capable, essentially young despite their chronological age. Their brains showed reduced inflammation, improved neural connectivity, enhanced learning and memory, all the markers of youth restored in elderly animals. It was like biological time had run backward, like they'd been given a second youth. This isn't the first recent breakthrough in aging research, but it might be the most significant. Several approaches are converging simultaneously toward the same goal. Radical life extension, not just adding years to life but adding youthful, healthy, functional years. Senolytics, drugs that selectively kill senescent cells that accumulate with age and promote inflammation and tissue dysfunction. Partial cellular reprogramming, techniques that reset cellular age without changing cell identity. NAD+ boosters that restore mitochondrial function and cellular energy production. Each approach targets different aspects of the aging process, but they all point toward the same possibility. Aging might be a treatable condition rather than an inevitable fate. We might be the last generation to die of old age, or at least the last generation to die of old age at 80 or 90. Our children or our grandchildren might routinely live for centuries, remaining healthy and vigorous for time spans that seem impossible today. Think about the implications for human civilization. Everything about how society is structured assumes limited lifespans. Education in youth, career in middle age, retirement in old age, death before 100. That pattern has held throughout human history. But what happens when people remain productive and capable for 200 years? For 500? For longer? Population dynamics would transform completely. Birth rates might need to decrease dramatically to avoid overpopulation. Generational wealth would accumulate on timescales we can't currently imagine. People could pursue multiple entirely separate careers, could master multiple disciplines, could think and plan in truly long-term ways. Someone who expects to live for centuries wouldn't dismiss climate change or resource depletion as problems for future generations. They would be future generations. But here's where things connect to our larger questions about extraterrestrial intelligence and interstellar exploration. Interstellar travel, using any technology we can currently imagine, takes a long time. Even traveling at 10% of light speed, an enormous velocity requiring revolutionary propulsion systems, reaching the nearest star system would take over 40 years. Reaching more distant stars could take centuries or millennia. For species with human-like lifespans, interstellar exploration seems nearly impossible. How do you crew a mission that takes longer than any human lives? Generation ships, where multiple generations live and die during the journey. Suspended animation, freezing travelers and hoping revival is possible? These solutions seem desperate, risky, unlikely to work. But for species that live for thousands of years, species that solved the aging problem millions of years ago, interstellar travel becomes straightforward. A 500-year journey isn't a multi-generational odyssey. It's a long trip, certainly, but entirely within the lifespan of individual travelers. You could visit another star system and return home to your original civilization, to friends and family who remember you leaving. If we're being visited, if 3I/Atlas represents probe or ship from an extraterrestrial civilization, they would almost certainly have mastered aging. Biological immortality or near immortality might be a prerequisite for any civilization that engages in interstellar exploration. And we're taking our first steps toward that capability now in 2025, achieving the early breakthroughs that could eventually lead to radical life extension. Is that significant? Is there something about reaching this level of biological understanding that makes a species interesting or worth observing? Are we crossing multiple thresholds simultaneously, technological and biological, that mark us as a civilization worth attention? The ethical implications of life extension deserve serious consideration. If aging becomes treatable but the treatments are expensive, we might create a permanent underclass who continue dying on normal timescales while the wealthy live for centuries, accumulating power and resources across generations. That inequality would be more fundamental, more permanent than any that exists today. Access to life extension technology might become the defining political issue of the next century, more consequential than any current ideological division. Would governments provide anti-aging treatments as basic healthcare? Would there be age limits, lotteries, selection criteria? Who decides who gets to live for centuries and who doesn't? Religious and philosophical implications are equally profound. Much of human culture, from art to religion to social structures, has developed around mortality, around the knowledge that life is finite and precious specifically because it ends. What happens to meaning when death becomes optional? What happens to urgency, to drive, to the intensity that comes from knowing time is limited? Some philosophers argue that mortality gives life meaning, that removing the deadline would drain existence of purpose and intensity. Others counter that this is simply rationalization, making a virtue of necessity, convincing ourselves we want what we can't change. If aging actually becomes treatable, we'll discover which perspective is correct, whether humans find meaning in indefinite lifespans or whether immortality produces existential malaise. But from a purely practical standpoint, from the perspective of a species that might aspire to explore beyond our solar system, to establish ourselves among the stars, to become a truly spacefaring civilization, radical life extension seems nearly essential. The timescales of space exploration, even within our own solar system, strain normal human lifespans. A round trip to Mars takes years. A mission to Jupiter or Saturn takes decades with current propulsion technology. Anything beyond requires either breakthrough propulsion systems or very long-lived crews. If we develop both fusion power and radical life extension in the next few decades, if we solve both the energy problem and the lifespan problem, humanity could begin seriously contemplating interstellar exploration. Not with generation ships or suspended animation, but with missions crewed by individuals who expect to live long enough to complete journeys lasting centuries, to explore distant stars and return to share what they've learned. We would be starting down the same path that any interstellar civilization necessarily traveled. We would be developing the foundational capabilities that enable expansion beyond a single star system. And if there are older civilizations out there, civilizations monitoring emerging species, watching for the signs that a new player is entering the cosmic arena, wouldn't these developments, these breakthroughs, these crossings of fundamental thresholds, be exactly what would attract their attention? The pattern becomes harder to dismiss as coincidence. 3I/Atlas arrives just as we achieve quantum error correction, just as we sustain fusion plasma for meaningful durations, just as we discover thousands of exoplanets and begin searching for biosignatures, just as we reverse aging in living organisms. The convergence feels meaningful, like multiple trajectories intersecting at a single point in history, like something orchestrated or at least noticed. Of course, this might be selection bias. We notice 3I/Atlas because we've developed the telescopes to detect it. Previous interstellar visitors might have passed through unobserved simply because we weren't looking, weren't capable of detecting them. Maybe interstellar objects are common, maybe they pass through regularly, and we're just now developing the observational capabilities to notice them. But 3 in 8 years, after all of human history without detecting any strange coincidence. And when you add the remarkable orbital alignment, the unusual composition, the anomalous characteristics, the pattern feels significant. Something might be happening that we don't fully understand yet, something that connects these developments in ways we're only beginning to perceive. Let me share one more breakthrough before we tie everything together into the larger picture that's emerging. The European Space Agency recently released findings that have the aerospace community buzzing with excitement and urgency. Their analysis of long-term microgravity effects on human physiology reveals both challenges and unexpected opportunities for future space exploration, and the implications extend far beyond simply enabling trips to Mars or establishing lunar bases. We've known for decades that prolonged exposure to microgravity causes significant physiological changes. Bone density decreases at rates of 1 to 2% per month, similar to osteoporosis but much faster. Muscles atrophy despite exercise regimens. Vision degrades as fluid shifts in the skull increase pressure on optical nerves. The cardiovascular system adapts to operating without gravity, which sounds fine until astronauts return to Earth and their hearts struggle to pump blood against gravity they've forgotten how to fight. But the ESA data reveals something we didn't expect, something that changes the calculus of long-term space habitation. Certain biological adaptations that occur in microgravity might actually be advantageous for a spacefaring species. The cardiovascular changes that are detrimental for returning to Earth might be optimal for permanent life in space. The bone density loss that causes problems under gravity doesn't matter in microgravity where bones don't bear weight. The vision changes might stabilize at a new equilibrium adapted to space environments. In other words, humans might naturally evolve, or could be medically adapted, into distinct forms optimized for different gravity environments. Earth-adapted humans with dense bones, strong hearts, and physiology optimized for 1G. Space-adapted humans with lighter skeletons, different cardiovascular systems, vision and vestibular systems calibrated to microgravity. Mars-adapted humans optimized for 38 centimos. Moon-adapted humans for 0.165 G. This isn't science fiction speculation. This is medical data pointing toward a future where humanity might diverge into distinct subpopulations adapted to different environments, different gravity wells, different planetary bodies. We could become a multi-planet species not just in terms of where we live, but in terms of biological adaptation to those environments. The ethical questions are immediate and concerning. Would space-adapted humans be able to return to Earth? Would they want to? Would we be creating permanent populations who can never visit the homeworld, who are locked into space habitats or low-gravity planets for their entire lives? How would societies develop among populations that literally cannot occupy the same physical spaces, that are biologically incompatible with each other's environments? But from a practical standpoint, this might be how spacefaring civilizations actually develop. Not by building spacecraft that perfectly replicate Earth conditions, not by shielding inhabitants from the effects of different gravity regimes, but by allowing or encouraging adaptation to those environments, embracing the changes rather than fighting them, becoming species that are native to space rather than visitors from a planetary surface. Any civilization that has achieved interstellar travel, that has spread across multiple star systems, would likely have undergone such divergence millions of years ago. They might not even be a single species anymore in any meaningful biological sense. They might be a family of related species, all descended from a common ancestor, each adapted to different environments, different planets, different conditions. If 3I/Atlas carries occupants, if there are beings aboard or associated with it in some way, they might be so adapted to interstellar space, to the conditions of long-duration travel, that they would be completely incompatible with planetary surfaces. They might not be able to survive in gravity, in thick atmospheres, in the conditions we consider normal. They might be native to space in ways we're only beginning to understand are possible. This adds yet another layer to the Fermi paradox, another possible explanation for why we haven't detected obvious signs of extraterrestrial intelligence. We might be looking for the wrong signatures, expecting civilizations that look like us, that build structures we would recognize, that use technologies familiar to us. But truly spacefaring civilizations, species that left their birth planets millions of years ago, might have become so different, so adapted to space environments, that we wouldn't recognize them even if we encountered them directly. Their technology might be biological rather than mechanical, grown rather than built. Their structures might be living organisms modified to survive vacuum and radiation. Their communication methods might use channels we haven't discovered or haven't learned to monitor. They might be all around us, common throughout the galaxy, and we simply don't recognize them as technological civilizations because they don't match our preconceptions. The discoveries of 2025, taken together, paint a picture of a species on the verge of fundamental transformations. We're developing technologies that could solve our energy problems permanently, that could extend lifespans indefinitely, that could enable permanent habitation of space and other planets, that could give us computational capabilities orders of magnitude beyond anything previously possible. We're discovering that our galaxy contains billions of potentially habitable worlds, that the universe is far more populated with planets than we ever imagined. And at this precise moment in our history, at this unique juncture when we're transitioning from a purely planetary species to something more, interstellar objects are arriving in our solar system with unusual frequency and displaying characteristics that challenge our understanding of what natural phenomena can produce. Is this meaningful? Is there a connection? Or are we pattern-seeking primates finding significance in coincidence, seeing intention where only randomness exists? The scientific method demands we remain open to all possibilities until evidence allows us to eliminate options. And so far, the evidence doesn't conclusively eliminate anything. Natural comet with unusual properties? Possible. Interstellar probe from advanced civilization? Also possible. Something else entirely that we haven't even conceived of yet? Can't be ruled out. What we can say with certainty is this: we're living through an extraordinary moment. A period when multiple technological and scientific frontiers are being crossed simultaneously, when our understanding of the universe is expanding at an unprecedented rate, when possibilities that seemed like distant speculation are becoming immediate engineering problems to solve. Whether or not 3I/Atlas is artificial, whether or not we're being observed by extraterrestrial intelligence, whether or not any of the more exotic theories prove correct, humanity stands at a threshold. The choices we make in the next few decades, the technologies we develop, the social structures we build, the priorities we embrace, will determine what kind of civilization we become, whether we successfully navigate the challenges ahead or stumble and fall back. Every technological breakthrough brings new capabilities and new risks. Maybe that's what 3I/Atlas is, if it's artificial. Not an invasion force or a threat, but an observation post, something sent to watch and record what happens when a species reaches this critical juncture. Maybe they've watched countless civilizations reach this point, seen most of them fail, seen the rare few succeed and join the community of spacefaring species. Maybe we're being evaluated, assessed, observed to see what choices we make, whether we handle these technologies wisely or allow them to destroy us. Or maybe, and this is perhaps the most sobering possibility, maybe this is first contact. Not the dramatic landing on the White House lawn that science fiction prepared us for. Not ambassadors emerging from flying saucers to shake hands with world leaders, but something more subtle, more ambiguous. An object entering our solar system with characteristics that force us to confront the possibility of intelligence beyond Earth, that make us question our place in the universe, that initiate a global conversation about what it means that we might not be alone. Maybe first contact isn't supposed to be unambiguous. Maybe the universe or advanced civilizations within it operate under some kind of prime directive, some protocol where emerging species aren't given definitive proof until they reach sufficient maturity to handle the knowledge. Maybe 3I/Atlas is designed to be exactly this, ambiguous, to be plausibly natural or plausibly artificial, to provoke exactly the debates and discussions and analysis that we're having right now. We're being presented with a question. What do you think this is? How do you react to ambiguity and uncertainty? Do you insist on definitive proof before considering possibilities? Do you reject anything that challenges your worldview? Or do you remain open, curious, willing to follow evidence wherever it leads, comfortable with uncertainty while you gather more information? Maybe that's the test. Maybe how we handle this ambiguous situation reveals something essential about whether we're ready to join the cosmic community, whether we've matured enough to think beyond our narrow provincial concerns, whether we can cooperate globally to address questions that affect our entire species. The next few weeks will be revealing. When 3I/Atlas emerges from behind the sun in early November, when our telescopes can observe it again without solar interference, we'll gather data that should help resolve some mysteries. We'll measure its trajectory with greater precision, analyze its composition in more detail, observe how it behaves as it approaches and then departs our solar system. If it's natural, we'll likely find evidence that conclusively points to natural origins, composition that matches predictions for objects formed in distant star systems, behavior that aligns with established models of cometary activity, trajectory that, while unusual, remains within the bounds of what natural gravitational interactions can produce. If it's artificial, well, that's when things get truly interesting. Any deviation from predicted natural behavior, any sign of course correction or active guidance, any detection of artificial structures or organized patterns would immediately become the most important discovery in human history. Everything would change. Not slowly, not gradually, immediately and fundamentally. The November 21st through December 5th window that has conspiracy theorists so concerned does represent a scientifically significant period. This is when any theoretical deployments would be most likely to occur, when any smaller probes released during the object's passage behind the sun would reach positions throughout the inner solar system, when we would have the best opportunity to detect whether anything unusual is happening. Major astronomical surveys are planning continuous monitoring during this period. Every anomaly will be investigated. Every unexpected detection will be analyzed. If something extraordinary is going to happen, if there's any truth to the more speculative theories, this is when we'll know. But regardless of what we discover about 3I/Atlas specifically, the larger pattern remains. We're experiencing a convergence of breakthroughs across multiple domains simultaneously. We're transitioning from a purely planetary species to something more ambitious, more capable, more technologically sophisticated. We're learning that the universe might be teeming with potentially habitable worlds, that life might be common rather than rare, that we might be joining a cosmos far more populated than we realized. These are the facts independent of any speculation about alien visitors. These are the verified, documented, peer-reviewed discoveries that are transforming our understanding of our place in the universe and our potential as a species. And really, regardless of whether 3I/Atlas is natural or artificial, regardless of whether we're alone or observed, these developments represent the story that matters. Humanity is growing up. We're developing capabilities that previous generations could barely imagine. We're solving problems that seemed insurmountable just decades ago. We're reaching toward possibilities that have existed only in science fiction and philosophical speculation. The universe is vast beyond comprehension. Over 90 billion light-years in observable diameter, containing trillions of galaxies, each hosting hundreds of billions of stars, each potentially surrounded by multiple planets. The scale is so immense that human minds struggle to grasp it. We use numbers and analogies and comparisons, but we can't truly comprehend what trillions of galaxies means, what implications flow from that scale. But here's what we know with certainty. In all that vastness, on at least one small rocky planet orbiting an unremarkable yellow star in a quiet spiral arm of an average galaxy, life emerged. Single-celled organisms somehow appeared from chemistry, through processes we still don't fully understand. Those simple cells evolved over billions of years into complex multicellular organisms. Life crawled onto land, developed nervous systems, brains, intelligence, consciousness. One species among millions developed language, abstract thought, technology, science. They figured out how the universe works, decoded the laws of physics, explained chemistry and biology and geology. They built civilizations, created art and music and literature, developed mathematics that allows them to describe reality with extraordinary precision. And now, just a few 100,000 years after emerging as a distinct species, just a few thousand years after developing agriculture and civilization, just a few decades after achieving spaceflight, that species is discovering thousands of other worlds, solving aging, developing quantum computers, achieving fusion power, sending instruments throughout their solar system, and contemplating their place in a cosmos that might be populated by countless other civilizations at various stages of similar journeys. That story, that trajectory, that incredible arc from single cells to interstellar aspirations is astounding regardless of whether anyone else is watching. Is meaningful independent of whether 3I/Atlas is natural or artificial. Humanity's emergence as a technological species, our development of science and our growing understanding of the universe, represents something genuinely remarkable in cosmic history. If we are alone, if Earth is the only place where life developed intelligence and technology, then we carry responsibility for something precious and rare. We become the universe's way of understanding itself, consciousness emerging from unconscious matter, meaning arising from meaninglessness. Our survival and success matter not just to us but cosmically, because we might represent the only place where the universe has woken up and started asking questions about its own nature. If we're not alone, if the universe teems with life and intelligence, if 3I/Atlas does represent first contact or observation from older civilizations, then we're about to discover we're part of something much larger than ourselves, that our struggles and triumphs are echoed across countless worlds, that the story we're living has been lived millions of times before and will be lived millions of times again. We would gain perspective, context, understanding of our place in a populated cosmos. Either way, we win. Either way, the truth is extraordinary. Either we're alone and therefore precious beyond measure, or we're not alone and therefore part of a cosmic community of incomprehensible scope and diversity. There's no outcome where the truth is mundane or disappointing. So as 3I/Atlas continues its journey through our solar system, as November approaches and our instruments prepare for intensive observation, as scientists around the world analyze data and debate interpretations and prepare for whatever discoveries await, we should recognize the privilege of living through this moment, of being present during this unique period in human history. Whether we look back on 2025 as the year everything changed, as the year we made first contact and joined the galactic community, or whether we look back on it as simply another step in humanity's gradual expansion of knowledge and capability, it's a remarkable time to be alive, a fascinating moment to be conscious and aware and able to witness these developments. If you've made it this far, if you've watched through this entire deep dive into the mysteries and breakthroughs of our current moment, you're exactly the kind of thoughtful, curious, engaged person this world needs more of. You're someone who wants to understand rather than just have opinions, who values evidence and careful reasoning, who can sit with uncertainty and ambiguity without demanding premature conclusions. So here's what I need you to do right now. First, hit that like button if you haven't already. This video took enormous effort to research, to organize, to present in a way that's both accessible and comprehensive. Your like tells YouTube this content matters, that people value deep analysis over shallow clickbait, that there's an audience for serious exploration of important topics. Second, leave a comment telling me you made it to the end. Just type, "I finished" or "watched completely," or share what insight resonated most with you. This serves two purposes. It shows me who actually engaged with the full content rather than just clicking and leaving, and it trains the algorithm to understand this video is worth promoting, worth showing to more people, worth amplifying beyond my current subscriber base. Third, subscribe if you're not already subscribed, and turn on notifications so you don't miss what comes next. As November approaches, as we gather more data about 3i/Atlas, as these various scientific developments continue unfolding, I'll be providing updates, analysis, connecting new information to the framework we've built here. And fourth, consider sharing this video. Not mindlessly posting it everywhere, but thoughtfully sending it to specific people you know who would appreciate this level of depth and analysis, who are curious about these questions, who would benefit from understanding the extraordinary moment we're living through. One targeted share to the right person has more value than 100 thoughtless posts to general social media. We're building a community here of people who think deeply, who question carefully, who remain open to possibilities while demanding evidence. That community grows one person at a time through intentional engagement and thoughtful sharing. Be part of building something worthwhile, something that raises the level of discourse, something that makes understanding more valued than certainty. The universe is revealing its secrets gradually, at a pace determined by our ability to ask good questions and interpret answers correctly. We don't get to demand truth on our schedule, don't get to force reality to conform to our preferences or timelines. We get what careful observation and rigorous analysis can uncover, when patience and ingenuity allow us to see clearly. But that's exactly as it should be. Easy answers would be suspect. If proof of extraterrestrial intelligence were obvious and unambiguous, if advanced technology were simple to develop, if understanding the universe required no effort or insight, we would have reason to doubt whether any of it was real. The difficulty, the ambiguity, the need for careful analysis and patient accumulation of evidence, these are signatures of genuine discovery rather than wishful thinking or self-deception. So we watch and we wait and we analyze and we remain open to whatever truth emerges from careful study. We don't prejudge. We don't insist on conclusions before evidence warrants them. We remain humble about how much we don't know while celebrating how much we've learned. 3i/Atlas will leave our solar system in the coming months, accelerating back into interstellar space, returning to the darkness between stars from which it emerged. If it's natural, it will carry samples of our sun's influence, molecules altered by passing through the inner solar system, cosmic rays from our local environment. If it's artificial, it might carry data about humanity at this precise moment in our history, observations of a species standing at a threshold, poised between planetary childhood and cosmic maturity. Either way, it will be gone soon, another brief visitor passing through, leaving us with questions and debates and memories of the time when something mysterious entered our cosmic neighborhood and made us wonder whether we were being observed, whether we were alone, whether the universe had noticed us. But the developments that accompanied its visit, the breakthroughs in fusion and quantum computing and aging research and space medicine and exoplanet discovery, these remain. These are permanent additions to human capability and knowledge. These are the foundations we're building our future upon, the capabilities that will determine what kind of civilization we become. That's the real story of 2025. Not whether one ambiguous object is natural or artificial, but whether humanity successfully navigates the transition from planetary species to spacefaring civilization, whether we solve the challenges threatening our survival, whether we build technologies that improve life rather than destroy it, whether we mature enough to handle the capabilities we're developing. The universe is watching, or maybe it isn't. But either way, we're accountable for what we do with this moment, with these capabilities, with these opportunities. We're writing a story whose outcome isn't determined, whose ending we get to choose through our actions and decisions and priorities. Make it a good story. Make it one worth telling. Make it one that justifies our existence, that validates the billions of years of cosmic evolution that led to this moment, that honors the sacrifices and efforts of every generation that came before us and built the civilization we inherited. We're alive at the most important moment in human history. Everything changes from here. What we do matters. Pay attention. Stay curious. Think carefully. And watch the skies, because November is coming, and we might finally get some answers. Thank you for watching. Thank you for thinking. Thank you for being the kind of person who values understanding. Keep looking up. Keep asking questions. Keep seeking truth wherever it leads. The adventure is just beginning.